So we're going to start talking about transformations. Anybody a fan of the Transformers? Did you have the little toys when you were little? Who's your favorite Transformer? Optimus Prime. I was not big into Transformers, but my nephew was, and my sister, being his mom and watching lots of Transformers with him, became a huge Bumblebee fan. I did not know she had this kind of secret obsession until we went to Universal Studios together. They have a Transformers ride there. I enjoyed that one, thought it was pretty cool. And so, what do Transformers do? They turn from robots to cars and back again, right? And so they're named Transformers because that's literally what this word means. Trans means to move or change. Form means shape. So to transform means to move shapes. Now, you studied transformations back in geometry when you did translations, rotations, reflections, dilations of shapes. So I want you to make that connection in your brain, but we're going to be focusing on transformations of functions. So we're not going to just take a shape and transform it. We're going to be looking at a function and how it transforms. Now, you did this in Algebra 2. Okay? But what I want you to do is don't just shut off your brain and think, oh yeah, I know all this already. I want you thinking, instead of thinking about the what, because you probably already know the what, I want you thinking about the why and the how. How is the equation connected to the graph? How is the graph affected by the equation? Because you already know this at a surface level, I want you to view it from a slightly different perspective and really be thinking about the why and the how as we go through these. All right, so we're going to start with a big picture, and then we're going to kind of zoom in on each different type of transformation. So if I have a function f of x, okay, so some function is performed here. And then I take g of x as a transformation of that. And I'm going to have a times f of bx minus h plus k. This then shows me the location of each of these different variables will produce a different movement in the function. So the h and the k are both going to produce translations. So the graph will translate. That means it will slide. We also call a translation a shift. The K is going to affect a shift vertical, and an H will be horizontal. Notice here that the H and the K are adding. This one's adding. This one is subtracting, but subtracting is just adding the opposite, right? So there's an additive element here, and adding causes a translation. Now, the A and the B are responsible for two different types of movements. One, they can be responsible for a reflection flip, and the reflection happens when there's a negative where A or B are. And the other thing A and B cause is a dilation. when things dilate, they change sizes. And so graphically, we talk about them being a stretch or a compression, stretching or compressing. So back in geometry, when we had a dilation, we had a closed figure, and we said that that dilated and it made an enlargement or a reduction. When we talk about the functions dilating, we talk about them stretching or compressing. So it's the same idea with a little different vocabulary. The A is going to cause vertical stretches and compressions, and the B is going to cause the horizontal ones. So that right there gives you like an overview, a summary of the different transformations. All right. So let's focus in on translations. Now the other thing that we want to be able to do is we want to be able to graph parent functions. So as we do our different examples, I'm going to use different parent functions so that we can look at those. So I'm going to start with a parent function f of x being the absolute value of x. So again, if you have forgotten, those two lines like that are for absolute value. Absolute value is the distance from 0 on the number line. And everybody should be able to graph the absolute value function. That is a skill you should have. So we're going to come here and make some ordered pairs. If I have x and f of x. So if I input a 2, the absolute value of 2 is 2. So it's 2 units from 0 on the number line. If I input a 1, the absolute value is 1. If I input a 0, the absolute value is 0. If I input a negative 1, the absolute value of negative 1 is positive 1. Because negative 1 is one space away from 0 on the number line. Doesn't matter if it's going left or right, it's just your number of spaces. Absolute value of negative 2 is 2. So we want to come in here and graph those 5 ordered pairs. 0, 0, 1, 1, 2, 2, negative 1, 1, negative 2, 2, and the absolute value is a V shape. I'll label that f of x. Okay, so then in a different color, I'm going to come here and have g of x, which is going to be a transformation of f of x. We're going to equal the absolute value of x plus 2. So I'm going to come here and add a column on my table for g of x. Alright, so as we fill this in, if I plug in a 2, 2 is my input. So the absolute value of 2 is 2, and then I add 2 more, and that gets to 4. If I plug in a 1, the absolute value of 1 is 1, and then I add 2 more, and that's 3. If I plug in a 0, the absolute value of 0 is 0, and I add 2 more, and that's 2. If I plug in a negative 1, the absolute value of negative 1 is positive 1, and I add 2 more, and that's 3. I plug in a negative 2, the absolute value of negative 2 is 2, and I add 2 more, and that's 4. So I'm going to come graph these points. 2, 4. So I'm graphing input and output now. So 2, 4. 1, 3, 0, 2, negative 1, 3, and negative 2, 4. And now this is g of x. So in words, what happened when we transformed, when we moved from f of x to g of x? What happened? We shifted up 2 units, right? Take any point on here, and you can see that what we did was we shifted up 2 units. So in general, when this value of k is greater than 0, we shift up. And when the value of k is less than 0, we will shift down. And again, that is something that most of you knew already, that would happen. But look at the why is it happening. This 2, I am plugging the x in, and I'm doing the function, and then I'm adding 2 more, and so I'm making the output increase by 2. So I'm making my output increase by 2. So if I look at this ordered pair, I have 2, 2 compared with 2, 4. The output is what's going up, and that's causing the vertical shift. All right. So now, let's change our parent function. Let's have a parent function of x squared. Right? That's your parent for your quadratic function. We should be able to graph that. Again, if I make a table of x and f of x values, when x is negative 2, negative 2 squared, positive 4. When x is negative 1, negative 1 squared is 1. When x is 0, 0 squared is 0. When x is 1, 1 squared is 1. When x is 2, 2 squared is 4. So I'm going to plot these points on my graph. So this creates a parabola. This is curved. This is not a V shape like the absolute value. So I have a parabola with a vertex at 0, 0. So, in another color, I'm going to do a translation. H of x is equal to parentheses x minus 2 squared. So I'm going to come in here and make a table, column in my table for my h of x values. So when I plug in negative 2 minus 2 is negative 4, and negative 4 squared comes out to be 16. And when I plug again a negative 1 minus 2 is negative 3, and negative 3 squared is 9. When I plug in a 0, 0 minus 2 is negative 2, and negative 2 squared is 4. When I plug in a 1, 1 minus 2 is negative 1, and negative 1 squared is 2. When I plug in a 2, 2 minus 2 is 0, and 0 squared is 0. And now I'm looking, this 16 and this 9, they're going to go off my graph. So I'm going to add another point. I'm going to put in a 3. 3 minus 2 is 1, and 1 squared is 1. So I'm not going to plot the 16 or the 9 because they're off my graph. I'm going to plot these 4 points. So at 0, I'm at 4. And at 1, I'm at 2. And at 2, I'm at 0. And then at 3, where did I go wrong here? This one, because you got to catch me. 1 minus 2 is negative 1. Negative 1 squared is 1, not 2. And then 3, 1. And can you see our parabola coming like this? So in words, what happened? This is my h of x. How did I move? To the right 2? Did you notice the difference? Here, I input my value, performed a function, and then added 2 before I got the output. Whereas over here, I input my value, and I did the subtract 2, and then I did the function. So this right here is altering the input before the function is performed. Whereas here, the 2 was being added after the function was performed. Now, I have often had people say, Ms. Collier, it says minus. Wouldn't minus mean go to the left? So let's be clear what we have here. If h is greater than 0, so if h is a positive number, we go to the right. And if h is less than 0, we go to the left. So like right here, what is my value of h? If I have x minus 2, h is equal to 2. Because the equation has minus in it. But if I had x plus 2 squared, I need to see that in my mind as x minus negative 2 squared. So then my h is going to be negative 2. And so this would go left. All right, take a pause and get a partner from your group to talk to. And one of you talk about the vertical and one of you talk about the horizontal. When we talk, we learn. Talk to each other.
There's ways to check it out.
Alright, so guys, skills that you want to have with this information, like say this information is just here, but there's actually a lot of different things to be able to do. So one is being able to look at a graph and describe the transformation in words. Another one is if you've given the graph, can you write the equation for the transformation? The other one is if you're given the equation, can you write the graph? Then the other one is if you have the graph, can you write the words that are going to describe what's going on? So you've got graph, equation, words, and you have to be able to navigate between all three of those formats. Alright, so now we're going to go on to reflections. Alright, we're going to do reflections pretty quickly. Alright, for my reflection, I'm not even going to look at an entire function. I'm just going to look at a point. Here's the point 1, 2. Alright, what if I'm going to reflect over the x-axis? So, reflect means to flip. So if I'm here at 1, 2, and this is my mirror line, and I flip over the x-axis, then I'm going to be here at 1, negative 2. So if I started here and flipped over the x-axis, like look at your ordered pairs. What happened? The y changed. The output changed, right? So that happens when I have some function f of x, and so when g of x equals negative of f of x. So when that negative is there in front, right, that's going to cause to reflect over the x-axis. Because I'm going to do my function, and then I'm going to take the opposite of it. And so the output is what's going to be the opposite. Alright, well what if I take the point 1, 2 and I reflect it over the y-axis? If I reflect it over the y-axis, it's here. What's that ordered pair? Negative 1, 2. How is that different from my original point? The x is the opposite. So this blue one is if I had h of x being equal to f of negative x. So if the input is what's negative, that's going to reflect over the y-axis. So again, I think it's very helpful when you're dealing with functions to think about input and output. Alright, let's pause again. Talk to your partner about the two different kinds of reflections. How are you going to tell them apart?
It was already moved, so they just ruined it. No, they threw it. Yeah, it was him.
Alright, let's come back together.
And then he dropped it, and then
Alright, so now we're going to talk about dilations. And what we mean by dilations is we mean to stretch or to compress. Alright, so let's go back to my our absolute value function. So we're going to start with f of x equals the absolute value of x. Alright? So we know that goes through 0, 0, 1, 1, negative 1, 1, 2, 2, negative 2, 2, makes this V shape. Alright, that's our parent function, f of x equals the absolute value of x. So I want to look at what happens if I have g of x, and g of x has 3 times the absolute value of x. So that means I'm going to multiply every output by 3. So I know it helps some of you to see it in a table. So we'll go ahead and do x, f of x. So I've got 2, 2, 1, 1, 0, 0, negative 1, 1, negative 2, 2. That's for my f of x. So then, g of x says, go ahead, plug this guy in to your input, and then take this absolute value and multiply it by 3, right? So it's going to be 3 times 2 is 6, 1 times 3 is 3, 0 times 3 is 0, negative 1 times 3 is, well, plug in a negative 1, you get out positive 1, and then you times 3 is 3. Plug in a negative 2, you get positive 2 times 3 is 6. So we call this a vertical stretch. And notice it involves multiplication as opposed to addition or subtraction. So we've got a multiplier there. And so if you kind of think about rubber bands, because they're something that stretches. So if I have a vertical stretch, come on, they thought. Right. So if I have a vertical stretch, I've got something that's staying anchored, and what I'm doing is I'm taking this value and I'm stretching it up, right? It's going to become skinnier in here, and I'm stretching. I have had students before who are like, Ms. Collier, I get confused of knowing, is this a translation up or is it a stretch? There's one point that's going to help you to know. Right there on the 0. Because if you add, the 0 is going to go up also. But if you multiply by 0, that's going to stay anchored at 0. Right? So when that 0 doesn't move, you know it's stretching. If the 0 goes up as well, then that's a translation. Alright, well what happens if on this same graph, I'm going to put h of x, and I'm going to have that be 1/3 x. So if I come in here in my table and I make h of x, so again, I'm going to evaluate the absolute value first. So I plug in a 2, I get out a 2, and then I multiply and I get 2/3. I plug in the 1, I take the absolute value, and then I multiply and I get 1/3. I plug in the 0, 0 times a third is 0, and I get 1/3 and I get 2/3. So on my graph, I'm going to go through 0, 0 again. When I'm on 1, I'm only on a third. And when I'm on 2, I'm only on 2/3. Over here, 1/3 and 2/3. So this h of x, this is a vertical compress. I like to envision somebody just came along on my f of x and just stepped on it and pressed it down, right? Can you envision that? There's your black one, and you just press it down. So to summarize here, if this is where the letter A is in my big formula, so if A is greater than 1, that's going to be vertical stretch. And if A is between 0 and 1, like the 1/3, that's going to be vertical compress. All right, now let's look at two other transformations. Let's suppose I had j of x. Let's say j of x is the absolute value of 3x. Well, let me look at my x's here. I plug in a 2. 3 times 2 is 6. I get out a 6. I plug in a 1. 3 times 1 is 3. 0, 3, 6. Do you see that this j of x is going to actually come out the same as the g of x? Now, that doesn't happen with all functions, but it's just because of the absolute value one. So this, though, this is a horizontal compress. All right, so I'm going to come in here and I'm going to make this the same color right here on the side. So I'm looking at this. So let's think about different perspectives. So I can, here's my f of x. When I had the red, it was stretching up. But the green is actually saying take the horizontal and press it together. Causes the same effect, right? So taking this and stretching it, or going horizontal and compressing it, gives us the same result. So when I'm looking at a graph, if I had this red-green graph and they asked me what happened, it could be a vertical stretch or it could be a horizontal compression. Graphically, they're the same. But equation-wise, they're different, right? And equations come from modeling the real world. So what's actually, the order of things happening can be different. But if you just in your mind think like this, that a vertical stretch a horizontal compression. Those have the potential to look the same. All right, so with our horizontals, that's going to be the letter B, right? And so, let's go. If B is greater than 1, that's going to be a horizontal compress. But if B is between 0 and 1, that's going to be a horizontal stretch. Now, actually, let's just pause there for a minute. All right. Go ahead and talk out with the partner the idea of stretch and compress.
At least in the equation is what's happening and what would be a stretcher. Reflection or dilation, it just depends. And that's today we're looking at crystal figures.
All right, so I want to consider one type of function that we know where the stretches horizontally and vertically, they're not going to look the same. And that's with our trig function. All right, so let's just go back a while. If you want to go ahead and just make a coordinate plane and mark these points, and we'll build a table here. All right, so if you remember our sine function, right? So we're going around the unit circle. Sine is the y value. So at 0, sine is 0. Then when we go up in the unit circle, the sine at pi over 2 is 1. And then we go around the unit circle, the sine of pi is 0. And then we're down on the, pointing down on the unit circle, the sine is negative 1. And then back around, so remember your sine function is a hill and a valley. You remember that? And we said that is one period, right? Goes from beginning and then back to 0 again. All right. So this 2, according to what we know, this 2 should cause a vertical stretch, right? So I'm going to go into my table and put g of x. So this means plug in. So sine of 0 is 0, and then 0 times 2 is still 0. Sine of pi over 2 is 1, and 1 times 2 is 2. Sine of pi is 0, and 2 times 0 is 0. Sine of 3 pi over 2 is negative 1, and negative 1 times 2 is 2. And then sine of 2 pi is 0, and 2 times 0 is 0. So all my zeros are still there. But at pi over 2, instead of being at 1, I go up to 2. And instead of being at negative 1 here, I go down to negative 2. Oh, I graphed that off a little bit, didn't I? That guy should have just went to right there. Now we're here at negative 2. All right, so you see the stretching effect? The 0 stayed still, and we stretched it, just like the rubber band. Yes, thank you for catching that. All right. But now let's look what happens from what we just figured out. If I have a 2 right here, actually let me change that right to not 2, let's say 1/2. No. I want to do, no, never mind, I want it to be a 2. Because we said that on our absolute value function, a vertical stretch is like a horizontal compression. But when we've got a sine function and we go and compress it, so now I'm going to go like this. 2 times 0 is 0, and the sine of 0 is 0. But 2 times pi over 2 is pi, and the sine of pi is 0. And 2 times pi is 2 pi, and the sine of 2 pi is 0. And 2 times 3 pi over 2 is 3 pi. Well, the sine of 3 pi, that's 0. And 2 times 2 pi, that's 4 pi, and the sine of 4 pi is 0. What, is that just like a straight line? No, I need to see what's happening in between. What's in between 0 and pi over 2? Pi over 4. So if I take pi over 4 and I multiply it by 2, that would be 2 pi over 4, which is pi over 2. Sine of pi over 2 is 1. And in between pi over 2 and pi, if I put in 3 pi over 4, and I multiplied that by 2, that would be 6 pi over 2, which is 3 pi over 2, which is going to be negative 1. So what happens now is I'm at 0, 0, 0, 0, 0, at 0, I'm at 0, and here at pi over 4, I got up to 1. And here at 3 pi over 4, I got down to negative 1. And so with our trig functions, when we do a horizontal compression, it changes the period. So when we have functions like absolute value that's going up all the way to infinity, and you press it in, right? It looks just like a vertical stretch because you're just stretching it, you're pressing it in, and it's just going to keep stretching up to infinity. But if you have something like a trig function, right, that has this top and this bottom, and you press it in, what it results is changing the period. So that's all to say that we made that statement that a vertical stretch can be like a horizontal compression in things like absolute value, but in your trig functions, they look very different. Right? It's just bringing back trig, you know.